As again, this class, as I did with the introductory, same book used before, Giancoli, either 6th or 7th edition. I'll be starting on chapter 15 today. Little review on chapter 14, which is from last semester. Again, check the syllabus, which is posted as far as the format of the class, how we're going to do labs. I'll talk about labs later on. We'll start the first one next week and go from there. So this is going to be on thermodynamics and energy as far as today. So moving on. All right, so from chapter 15, all right, this is thermodynamics. Which is basically the laws of dynamics is basically laws of energy, heat, and how we understand the process of those in gases primarily. Okay. So what we go back from before, or from earlier, we had kinetic energy is 1/2 mv squared, where m is the mass, v is the velocity speed squared, and we have the kinetic energy in joules. All right, so that's what we have for a single object. So an object moving at a particular speed and mass has a kinetic energy. All right, now when we deal with, that's fine dealing with small part, with the big particle. Well, how do you deal with gases? All right, we don't deal with one molecule at a time. Sometimes in quantum physics, you may deal with the dynamics of one particle, but in chemistry, we're dealing with an ensemble of particles in a container of some sort. So we need to deal with this whole package. And in that case, it's very difficult to measure the speed of an individual particle, or even the speed of any of them. So what we realized is that this is proportional to the temperature of the gas in degrees Kelvin. All right, again, Kelvin is Celsius plus 273, and we have the gas laws of PV equals nRT. P is the pressure, B is the volume, N is the number of moles, R is the gas constant, T is the temperature. All right, so going back to there, and T is the temperature in degrees Kelvin, so that absolute zero is 0, and at that point the pressure falls to 0. So that what we see is before, if we do a graph of pressure versus temperature, it's linear and goes to the point 0, 0. So the kinetic energy of a gas is proportional to the temperature. And we did that in chapter 14 as we talk about the internal energy of a gas, basically the energy of all the gas together, and that's given by 3/2 nRT, where 3/2 each degree of freedom, x, y, and z is a half, so we end up with 3, n is the number of moles, r is the gas constant, and T is the temperature. And again, this will be either in joules or calories, depending on what we're doing. Remember from also, we had Q is mc delta T, where m is the mass, c is the specific heat, and delta T is a change in temperature in either degrees Kelvin or degrees Celsius, and this was generally in calories. So that was back from chapter 14, all right? So from here, we also had this in chapter 14. So this is what we call the internal energy. And this will be primarily in joules. And we're not going to deal with the number of moles per se, but the internal energy does depend on number of moles we have. So in a container, number of moles, a gas constant, and temperature. But primarily, we're going to be dealing with a container that is sealed, so this doesn't change. So the only thing that'll change is if the temperature changes, the internal energy changes. Nothing else here will change. So this is proportional to that. Okay, so that's that part there. Again, that's back in chapter 14. And then we're going to deal with what we call, I'll leave that out for a minute. So now we're going to deal with what we call the first law of thermodynamics, and this is DeltaU. If we have a container of some sort that has a number of moles of gas and it's sealed, and the internal energy of the gas will depend on Q minus W, where U is the internal energy, Q is heat added, and W is work done by gas. So what would this mean if we just had a sealed box? Then we can't do anything, but what we're talking about here is if we have, say, a gas that has, say, a piston on top. So a sealed container that has a piston on top. And if the gas expands, work will be done doing it because it will lift up this container. So as the gas expands, like in an engine, right, it's hot, expands, does work, it's work done by it. So it's positive, this number is positive, work done, Q is positive, and we have the difference gives us the internal energy of the gas. So this is the first law of thermodynamics. So keep it in mind here. We'll be using this quite a bit. All right. So, okay. And we'll be looking at different cases of how this applies. So I'm going to go leave that up there, and I'll erase this for a minute. All right, so let's do an example. We and we'll be using this program, one of the PhET programs by University of Colorado that does exactly dealing with this concept. So when we have heat added would be Q, would be if we have some sort of flame that adds heat to the system, work is done when this lifts up. And then U is the internal energy of this gas. So an example, say we have a container, I just used the one in the book, so Q is 2,500 joules. We add 2,500 joules. And example there is W is 1,800 joules are done on the system. So actually it's being compressed. So if it's being done on it, it's going down, which means the work is actually negative. So this would be negative 1,800 joules. So delta U, so thinking about it intuitively, if we add heat to a gas, that will raise the internal temperature. And then if we compress it, much like a diesel engine, if you compress it, that will also increase internal energy. So these two should combine to make the internal energy higher. So this would be W delta U is 2500 minus 1800, which would be 4300 joules. Okay. So again, look at the question. It's work done on the system that does that. All right. So we're going to be doing this quite a bit, and we're going to look at certain processes here. And this will be a relatively short lecture today, because we're not going to get too much into the ideas of this. We'll talk a little bit about heat engines, but we're not going to talk about refrigerators and heat pumps, which have quite a bit of value because, you know, if you take differences, I mean, a heat pump is basically taking energy out of the earth and using that to run an engine basically for free. And a refrigerator is basically taking a heat engine in the reverse direction. So we're going to be dealing with a few things here. Work, again, delta U is 3 halves nRT. Q is just the heat added. Work is going to be defined as P times the change in volume. All right, so the work done. Because in a gas, the work, it actually has to move. So we have to have a change in volume. Whether the pressure changes or not is another, but to do work, it has to be if it's positive work, it's compressed, it's negative work. So we're going to be doing this, and part of it is, if we look at a graph of P versus V, all right, this again goes from the ideal gas law, what we had earlier. For those, if we have a constant pressure and volume, so the volume, say, increases from 1 liter to 3 liters, then the work done will be pressure times the change in volume, which will be the area under this curve. Now we get the calculus, so that's what it's straightforward there. The pressure is constant, the volume changes, and that's the work. If you want to get more complicated, if we have a process that does something more complicated, you know, we start getting into calculus, but this is still PV, the work is the work, the area under this curve. So that's what we talk about calculus sometimes, but we're just going to be doing this on an algebra basis. So the work done is the area under this graph. And we're going to look at different processes. This particular process is what we call isobaric, but we'll go through each of them because this one, the pressure is constant. All right, so leaving our expression up here, okay. Then erasing some of this. Okay. And also get rid of that. So I have a little more room to work with. All right. The first one we're going to be talking about is what we call isothermal. And in that case, isothermal, iso means constant, thermal is temperature. So what this means is a change in temperature is 0, which would mean the change in internal energy is 0. So if you have an expression like that, what that means is that delta U is Q minus W, or in other words, the heat added Q is just equal to W. So all the heat added goes into work, and that's a very efficient process. That also means a change in temperature is 0. That kind of process, going back to the ideal gas law, if change in temperature is constant, then this is all one constant, and then basically P is proportional to 1 over V. So for this to remain constant, as that goes up, this has to go down. So we'd see a graph that looks something like that, right? Where this is P and this is V, and the work done is still this type of process. So this is what we call an isothermal process. Okay. We'll get a little more detail of that. So this would be the work done, and that would be applied. So that's what we call isothermal process. And that's the first one. Okay. Next case, so I'll leave that up for a minute. Okay, so you can write that down. Next case is isobaric, which we just talked about briefly. And in that case, delta P is 0. So in that case, we would have, if we have a graph of P versus V, it would be straight like that, and that would be the work done. So in that case, right. Okay. So the work done would be just P times the change in volume, period. Next we have isovolumetric. In this case, delta V is 0. Isovolumetric change in volume is constant. P may change. So in that case, we would have a graph like this. That goes from this point maybe up to that point, and the area under a straight line, the volume, the work done, the work would be 0. So in that case, basically what would happen is if you have a container, right, and we have a piston, and we apply heat, this thing does not move, so work is 0. So all the heat would go into internal energy. So in that case, delta U is just Q. Okay. So all the heat would go into internal energy. It would just get hotter and hotter and hotter. That's the case there. Right, so those are the two isobaric, isovolumetric, relating to work. In that case, and then the final one, which a lot of times is the most desirable to try to do, which we see a lot, is what we call adiabatic. And in that case, what we have there is if you have a sealed container, say with a piston that goes up and down, and in this case, adiabatic is Q is 0. So no heat is applied to it. So the only change in temperature, the only change is, in this case, Q is 0, so delta U is minus W, all right? So what does that mean? All right, this could be like a diesel engine. Diesel engine doesn't apply any heat to it. what it does is you have a compressed gas. So the cylinder is compressed with a change in temperature. And as the gas expands, it does work on the system, but as the gas expands, an adiabatic process, gas expands, temperature goes down. So delta U, in this case, as if W is positive, then delta U is negative. And in that case, temperature T goes down. That's basically a principle of a refrigerator. You take the gas, kind of do work so it actually expands and the temperature goes down and that gas can be expelled. That's adiabatic. It's the same reason why the atmosphere is colder above, of adiabatic expansion of a gas. And so that's one of the more interesting processes. So that's that there. So we have 4 different processes. We have isothermal, which is delta T equals 0 because delta U is 0. So delta U is 0. Isobaric, W is P delta V, I should say. Isothermal, isovolumetric, W is 0, there's no work done, and adiabatic, which we just talked about. So those are the 4 processes we have here, and we'll be doing examples, some of those later on, as far as that's concerned. Okay. I should say one thing, when we talk about this P versus V graph, we do that, let's say go from point A to point B, isothermal, right? That's the work done as the volume expands. Now, in an engine, it goes through a cycle. It goes through, it closes, we have an engine, gas comes in, explodes, expands it, when it expands, the engine takes in more gas, compresses, explodes, and goes through the cycle again. So in this case, what we have, if we have a cycle where it comes down, so this is isovolumetric, goes across, and then back up, the actual area, the work done is actually the area under this part. So we go A to B to C to D, and then back up to A, this process, this is the work done. We don't include this because this is going back that way, so we subtract that. So this is the work done. There's already a picture of that in this example here. So this would be the work done in the book on page 417. You go through cycle A to B to D. You know, in that case, I'm going down where they go down a bit, but that would be a case there, go back up. That's the work done in that case. So that's a little bit on engines as far as that's concerned. Okay, and I will probably leave it, oh, let me do one more thing then. So this is the first law of thermodynamics. Last law, which we get into, and I'll leave this up. So this is the first law. So ideally, everything's efficient. But in reality, it never works quite that way. And the second law, which will do this briefly and quick. The second law is basically heat always flows to cold, but never the other way around. So if you have a container of gas, and you have hot gas here, and cold here. This gas will move to here, but theoretically it could go back there around, but it doesn't. Heat always flows from hot to cold. And that's the second law of thermodynamics, is that you don't have cold going back out. You open a window, the cold air comes in, the hot air goes out. That's just how, because cold air is denser, has less kinetic energy to it than hot air. So that's how it works. It'd be nice to do the other way around. We'll get into this when we talk about entropy, because it's related to that too. Because what we're going to do is, when we talk about this concept, is in an engine, right? We run an engine, we apply heat, a certain amount of that heat goes into work, but some of it is actually lost as cold. So I'm going to use the same terms they use in the textbook, Q high and Q low, because this definitely relates to temperature, but this is lost, and so the work done is Q hot minus Q low, where these are all going to be in joules. And then we define the efficiency of an engine as the work done over the applied heat, which is also the difference between Q hot, Q low, over the applied heat. Okay. So this is a number between 0 and 100%. So we have to multiply this by 100% to get a percentage as far as that's concerned. Of course, again, it's not easy to measure efficiency that way. We can also, again, there's a relationship between temperature and energy. From ideal gas law, we can also define this in terms of temperature, where if this is the temperature of the hot gas, and this is the temperature of the cold gas coming out, then the efficiency is also defined as T hot minus T low over T hot times 100%, where T is in degrees Kelvin. So that's the efficiency there is concerned. All right, so let me do one example here before I stop for the day. All right, so if you have an engine, so if you have, say, an engine, a car engine, you apply heat, for the gas, T hot, the gas is hot, say it's 600 degrees Kelvin, and it does work to turn the car, make it go, but there's an exhaust that comes out. This is a temperature to it. Now it's not absolute zero, it's going to be colder than it was there, but it's going to have, it's relatively warm. If you ever feel the exhaust of the car, and say this is, say it's room temperature, which is about 300 degrees Kelvin, okay? So you can check that yourself, that this is approximately room temperature. Remember, 273 is 0 degrees Celsius. And the efficiency of this engine would be T hot minus T low over T hot would be 600 minus 300 over 600. Let's cut it running out of room. And that would be 350%. That would actually be an extremely efficient engine. In reality, this is going to be probably hotter than that. And this may be hotter than that too. So it's very hot gas coming out. Say a temperature is really hot, like almost boiling. This would be, say, 400. And that would be 200. Then we're down to 33%, which is actually more typical for a car engine. All right, so that's the efficiency. And then we get into Carnot efficiency, which we're not going to get, which is dealing with the actual. So this would be a theoretical efficiency. So if the engine was 100% efficient, the gas coming out would be absolute zero. All the heat would go into the work. And that we know is not happening. All right, you don't have ice, liquid oxygen falling out the bag. So that's it there. And then the next part I'll deal with, I'll talk about that later, is on entropy and the second law of thermodynamics, and we'll get into that part. So there'll be a lecture I'll talk about on Tuesday. So this is the first lecture. It'll be posted. If you have any questions, the first problem set will be posted too, and we'll go from there.